Welcome to the Quantum to Cosmic YouTube channel with me, Ollie. Welcome back to this tutorial series on functions. This series is aimed at first year undergraduate university students or those who are just interested. Whether you just need a refresher on these topics or are learning them for the first time, you're in the right place. Today, we're continuing with partial differentiation, looking at the chain rule with partial derivatives, i.e. a function of a function. So if you're ready to learn, then let's get into it. Previously, we've had that u equals f of x, and if we had this being a function of a function, we therefore also have x equaling another function, let's say g of another variable t. And as a consequence, we can then say, well, du by dt by the chain rule is equal to du by dx times dx by dt. And that works fine. We have, therefore, f prime times g prime. But now if we consider a function of two variables, so u equaling u of x and y, where both x and y are functions of t, then the best way to start for finding this chain rule is to use the increment equations that we used in the last video. But we can say delta u, in this case, is approximately equal to partial du by dx times delta x plus partial du by dy times delta y. And now if we divide everything by some small delta t, and then take the limit as delta t and our other increments tend to 0, we'd have all our delta u, delta x and delta y divided by delta t. And then obviously as we take that small limit, this will become a total differential, so it will become du by dt equals partial du by dx times total dx by dt plus partial du by dy times total dy by dt. And that would be the chain rule for our partial differentials. And obviously here we're assuming that x and y are only functions of t, i.e. there is no other variable, they're not also got some partial differentials involved, so we can take this total differential for dy and dx. If, however, our functions x and y were of two variables, so x of rs and y of rs, then we'd have just a very similar thing to this chain rule, but we'd have two equations. We'd have partial du by our first variable dr, and that would equal partial du by dx. And then it is different here, we'd have another partial differentiation, so we'd have another partial derivative, so it'd be partial dx by dr, and then we have the same thing for y, so partial du by dy times partial dy by dr. Then we have the same exact equation, but r is replaced with s, and we just have those two equations for working out each our partial du by dr and our partial du by ds. So that would happen if we had multiple variables for our x and y functions, and obviously this can just keep iterating further and further. You can have these then be of r is then of another function, and it continues. So if we just think of an example, we could say some volume v of a cylindrical box of radius r and height h is going to be equal to pi r squared times our height h. And if we just, let's say that r is a function of t and it's equal to 2t, and then h is also a function of t and it's equal to 1 plus t squared, then we can use our chain rule to work out what is dv by dt. So if we do that, we'll have partial dv by dr, and then dr by dt, plus partial dv by dh times dh by dt. And so now if we do that, we'll have 2 pi rh times pi 2 for our first term. Then we have pi r squared times 2t. So if we times these brackets out and substitute in our values for r and h, we'll be left with 8 pi t plus 16 pi t cubed. And so, okay, that's all well and good. Let's check that that is correct. And in this case, it's quite simple for differentiating after we've substituted r and h into our original v equation, but it might not be this simplistic. So if we just calculate what v is in terms of t, we'd have pi times r squared, so 4t squared, times 1 plus t squared, just h. And if we times all that out, we'll be left with 4 pi t squared plus 4 pi t to the 4. And now if we do our dv by dt, it's 8 pi t plus 16 pi t cubed. And there you go, they do match, and therefore we can see that our chain rule is working as we should expect it to. And obviously in this case, as I was saying, this calculation down here is simpler, it's easier, you don't need to remember all the chain rule and everything, but obviously this is a very simple example. In the future you'll come across much more difficult ones where you can't do this just straight substitution to find v in terms of t and then differentiate it, and so the chain rule will come in handy a lot there. So for this example, we're going to be using u equals x squared y, where x is a function of s and t, where it's s times t, and y is also a function of s and t, where it's s plus t. So this is going to be using this bracket here, where we're going to be doing two chain rules to work out the different partial derivatives of u in this case. So for the first one, let's use partial du by ds, and that's going to be partial du by dx, partial dx by ds, and I won't say the rest, but you get the picture. And I'll leave it to you to do all of this differentiation, and it's quite simple, but times it all out and you'll see that this becomes 3s squared t squared plus 2s t cubed. So then if we do the same thing but for t, and again you can work out all the derivatives here, this will equal 3s squared t squared plus 2s cubed t. So very similar but not quite the same. And how will we check this? Well, like we did for v above, we can substitute in our x and y and do it manually that way without the chain rule. So we can say u is equal to x squared, so it's going to be s squared t squared times y, which is s plus t. If we times that out, that's going to be s cubed t squared plus s squared t cubed. So now du by ds is just going to equal 3s squared t squared plus 2s t cubed. And then du by dt will equal 2s cubed t plus 3s squared t squared. And if we just put this term in front of that one, it's exactly the same as above, and so is the du by ds. It's the same as before. So again, you can see this chain rule is working how we should expect it to, and so you can have confidence when using it for more complicated examples. So this last example is a cautionary example because you might get caught out if you do this incorrectly. So if we have a function u equaling xy plus y squared, and we also know that y is a function of x and another variable t, where it's y equals x plus t, then we can say obviously that this u is equal to x times x plus t plus x plus t squared. And that's great. If you wanted to work out now what is partial du by dx, then how do you do it? Is that equal to y if we take the first equation, or is it equal to 2x plus t plus 2 times x plus t? which is it? And these are not equal because y here is, we know it's equal to x plus t. And this simplifies to 4x plus 3t. So in both cases, we have partial du by dx. And which one is the correct one to use? Well, these differentials, these partial differentials are keeping different variables constant. So for the first example, what we're doing is keeping y constant. But for the second example, we're keeping t constant. These are different partial derivatives, and this will come up a lot in thermodynamics, where we're keeping different things like pressure or temperature constant when we're trying to vary another variable. They're the same function, and they'll have values at corresponding points, but this increment is, in the first case, it's keeping y constant when we're changing x, and in the second case, we're keeping t constant when we're changing x. So be very careful of this. It will come up, especially in thermodynamics, but it's just a good thing to know as well. Today, we've learnt about the chain rule with partial derivatives. In the next video, we'll be looking at partial differentiation for converting between Cartesian and polar coordinates. So if you want to learn more, I'll see you in the next one. If you learnt something new or just enjoyed this video, please hit the like button and don't forget to subscribe and tap the notification bell to stay updated on new videos. In the meantime, stay curious and I'll see you in the next one.